Tonight we're going to explore a question that has haunted humanity since we first looked up at the stars. A question that appears simple on the surface, but proves devastating in its answer. Why can't we travel beyond our solar system? This isn't about insufficient technology or limited budgets. We're dealing with something far more profound, something far more permanent. The fundamental laws of the universe appear to have constructed an invisible prison around us, a barrier that no amount of human ingenuity can break through. By the end of this journey, you'll understand exactly why we're confined to this tiny corner of the cosmos, possibly forever. Let's start with something you probably already know, but rarely comprehend in its true magnitude. The closest star to our Sun is Proxima Centauri, a red dwarf star, small and faint, located approximately 24 light years away. When we say light years, we're talking about the distance that light travels in one complete year, moving at 300,000 kilometers per second. That's approximately 9.46 trillion kilometers per light year. Proxima Centauri sits at 4.24 of those distance units away, which means roughly 40 trillion kilometers. Write it out like this: 40,000 kilometers. 40 trillion. This number is so vast that the human mind simply cannot process it meaningfully. Let's try to make this more tangible. The fastest space probe humans have ever built is the Parker Solar Probe, designed to study the Sun. At its maximum velocity, it reaches about 700,000 kilometers per hour when approaching the Sun. That's an incredible speed, faster than anything we've ever created. But even at that astonishing velocity, it would take more than 6,500 years to reach Proxima Centauri. Think about that for a moment. 6,500 years. When that spacecraft finally arrived, more time would have passed than has elapsed since the first pyramids of Egypt were constructed. The entire history of human civilization, written from ancient Sumeria to the present, would fit inside the travel time. And there would still be thousands of years left before arrival. And that's just the nearest star. The Milky Way, our home galaxy, measures approximately 100,000 light years in diameter. It contains between 100 billion and 400 billion stars. If we wanted to cross the galaxy from one extreme to the other, traveling at the speed of the Parker Solar Probe, it would take us approximately 150 million years. 150 million years. The dinosaurs went extinct 66 million years ago. You could begin that journey when dinosaurs still dominated Earth, travel through their entire era, witness their extinction, the rise of mammals, the evolution of primates, the emergence of humans, all of recorded human history, and you would still be only halfway to your destination. We're not talking about distances that are beyond our current technology. We're talking about distances that exceed biological timescales, geological timescales, even timescales on which species evolve. But perhaps you're thinking this is just a speed problem. If we could build faster ships, if we could approach the speed of light, maybe then we could do it. After all, light travels from Proxima Centauri to here in just 4.24 years. If we could travel at 10% of light speed, we'd arrive in 42 years. An entire human lifetime, certainly, but feasible. A young person could depart Earth and arrive at Proxima Centauri as an elderly individual. Difficult, yes, but not impossible. This is where reality begins to show us its most cruel limitations. Reaching 10% of the speed of light, 30,000 kilometers per second, isn't simply difficult with our current technology. It may be fundamentally impossible for any crewed vessel, regardless of how advanced our technology becomes. Let's talk about energy. The energy required to accelerate an object increases dramatically as you approach the speed of light. This isn't a technological limitation. It's a fundamental law of physics described by Einstein's special relativity. As an object moves faster, its effective mass increases. The faster it goes, the more energy is needed to accelerate it further. At velocities approaching light speed, the amount of energy required becomes absurdly large. Let's do some approximate calculations. Suppose we want to send a spacecraft weighing about 1,000 tons, roughly the mass of the International Space Station, to 10% of light speed. The kinetic energy necessary would be approximately 4.5 x 20 joules. To put this in perspective, that's roughly equivalent to the total energy consumption of all human civilization for several years. All the electricity generated by every power plant on the planet, every drop of fuel burned, every solar panel, every wind turbine operating continuously for years, just to accelerate one spacecraft to 10% of light speed. And that's just the energy to accelerate. You also need to decelerate when you reach your destination, which requires approximately the same amount of energy. So you're really looking at double that amount. And this assumes perfect efficiency, that every joule of energy you generate goes directly into accelerating the ship without losses. In reality, no system is perfectly efficient. Typical rocket engines have efficiencies of only a few percent. Even the most efficient theoretical systems we can imagine might have efficiencies of 50 to 70% at best. This means the actual amount of energy you would need to generate would be several times greater. So, where would we obtain all that energy? Traditional chemical rockets won't work. Chemical fuels simply don't contain enough energy per unit mass. If you tried using chemical rockets to reach even a significant fraction of light speed, the mass of fuel needed would be astronomical. In fact, you can calculate that no matter how much fuel you load, you could never carry enough to reach those velocities. The fuel mass grows exponentially with desired speed, and you rapidly reach a point where you'd need more fuel than the mass of entire planets. Chemical rockets took us to the moon, allowed us to send probes throughout the solar system, but they're completely inadequate for interstellar travel. What about nuclear propulsion? Nuclear fission releases approximately 1 million times more energy per unit mass than chemical reactions. A fission reactor splits heavy atoms like uranium or plutonium, releasing energy in the process. Nuclear fission engines have been proposed for decades. Project Orion, conceptualized in the 1950s and 1960s, proposed using nuclear explosions to propel a spacecraft. Basically, you would detonate nuclear bombs behind the ship, and the shockwave would push the craft forward. It sounds dangerous and impractical, and it is, but mathematically it could work. Estimates suggest an Orion-type engine could reach speeds up to 5% of light speed, maybe even 10% with very optimistic designs. That's better than chemical rockets, but you're still looking at voyages of 40 to 80 years to Proxima Centauri, and that's just the nearest star. Project Orion was never built, partly due to international treaties prohibiting nuclear weapons in space, but also due to immense engineering challenges. You would need thousands of nuclear devices, each detonating in perfect synchronization. You would need a shock-absorbing shield strong enough to withstand repeated nuclear explosions, and you would need to protect the crew from radiation. These problems aren't impossible in principle, but they're extraordinarily difficult. Even if you could overcome all these challenges, you're still limited by the amount of fissile material you can carry. Nuclear fission has its limits regarding how much energy it can produce per unit mass. So what about fusion? Nuclear fusion, the process that powers stars, could provide even more energy. Fusion combines light atoms, typically hydrogen, into heavier atoms like helium, releasing an enormous amount of energy. Fusion is the holy grail of energy production on Earth. We've been trying to build practical fusion reactors for decades, and while we've made advances, we still don't have a functional fusion power plant that produces more energy than it consumes. But suppose we solve fusion. Suppose we build efficient fusion engines for spacecraft. How much would that help us? Calculations suggest fusion engines could theoretically accelerate a ship to 10 or perhaps even 20% of light speed. That would reduce travel time to Proxima Centauri to 20 or 30 years. Still an entire human lifetime, but it begins to seem feasible. You could send a young crew, and they'd arrive in middle age or older. The problem is that building a fusion engine for a spacecraft is far more difficult than building one for a stationary power plant on Earth. On Earth, you can have massive, heavy reactors with enormous magnetic fields to contain the plasma. In space, every kilogram counts. You need an engine that's lightweight, compact, and produces thrust for years or decades without failure. You need fusion fuel, probably deuterium and helium-3, which are rare and difficult to obtain in large quantities. And you need to deal with the immense heat produced by fusion reactions. You can't simply radiate heat into the vacuum of space as easily as you might think. Vacuum is an excellent insulator. The radiators needed to dissipate heat from a fusion engine would be enormous and heavy. Even if we overcome all these obstacles, we still face another fundamental problem: fuel. A fusion engine needs to transport its fuel. Unlike an airplane that can refuel, an interstellar ship has no gas stations along the way. You have to carry all your fuel from the beginning. And the more fuel you carry, the heavier your ship becomes, which means you need even more fuel to accelerate it. This problem, known as the Tsiolkovsky rocket equation, establishes a fundamental limit on how much velocity you can achieve based on how much fuel you can carry. To reach truly high speeds, a very large fraction of your ship's mass must be fuel. At near relativistic velocities, most of your ship's mass would be fuel, leaving very little for payload, crew, life support, and ship systems. Here's a proposal that sounds clever. What if we don't carry the fuel? What if we collect it along the way? This idea is called the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The idea is to use a giant magnetic field to collect hydrogen from the interstellar medium, the diffuse gas that exists between stars. Then you use that hydrogen as fuel for a fusion engine. In theory, as long as there's hydrogen in space, your ship can keep accelerating indefinitely. You never run out of fuel because you're constantly collecting it. Sounds perfect, right? The problem is that interstellar space is incredibly empty. The average density of the interstellar medium is approximately 1 hydrogen atom per cubic centimeter. That's 1,000 trillion times less dense than the best vacuum we can create on Earth. To collect enough hydrogen to fuel a fusion engine, you would need an absolutely massive magnetic collector, probably thousands of kilometers in diameter. The mass of the magnets and equipment needed to generate such a large magnetic field would be tremendous. And as you accelerate, the drag caused by collecting all that hydrogen could slow you down more than the engine accelerates you. Calculations suggest Bussard ramjets might not work at all at realistic interstellar medium densities. It's a beautiful concept in theory, but practically impossible to implement. So fusion, even in the best case, only gets us to speeds of 10 to 20% of light speed. And that's assuming we solve enormous engineering challenges we haven't yet overcome. What about going faster? What about approaching light speed? This is where physics becomes truly ruthless. Antimatter is the most energy-dense substance we know. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. According to Einstein's famous equation, E by an mc2. No other process we know is as efficient. If we could use antimatter as fuel, we could theoretically accelerate ships to velocities very close to light speed, maybe 90% or even more. The problem is that antimatter doesn't exist naturally in usable quantities. We have to create it in particle accelerators, and it's absurdly expensive and difficult to produce. CERN, the world's largest particle physics laboratory, produces only a few nanograms of antimatter per year. A nanogram is 1/1000th of a gram. To fuel a spacecraft, you would need kilograms or even tons of antimatter. At current production rates, it would take billions of years to produce that quantity. Even if we could mass produce antimatter, storing it would be incredibly difficult. Antimatter annihilates instantly when it touches normal matter, so you need to store it in magnetic or electric traps that prevent it from touching the walls of any container. These traps require energy to function, and any failure would result in a massive explosion. Then there's the problem of using antimatter as propulsion. When matter and antimatter annihilate, they primarily produce gamma rays, photons of extremely high energy. Gamma rays are very difficult to direct or use for thrust. Most of the energy simply radiates in all directions, not pushing your ship forward. Converting antimatter annihilations into useful thrust is another massive engineering challenge. Even with antimatter, you're probably limited to speeds around 50 to 90% of light speed at most. Now, at velocities truly close to light speed, say 90% or more, the effects of special relativity become important. Time dilates for travelers. If you travel at 90% of light speed, time for you passes more slowly than for people on Earth. A journey of 10 years according to Earth clocks might feel like only 4 or 5 years to you. This is real, not science fiction. Clocks on ships would genuinely run slower. At even higher speeds, say 99.9% of light speed, time dilation becomes extreme. You could travel for decades or centuries according to Earth clocks, but for you, it might feel like only a few years. This could make long interstellar voyages more bearable for the crew. You could travel to distant stars without aging much, but there's a catch. While you experience only a few years, everyone on Earth ages normally. You return home after what seems like a 5-year trip, but on Earth, 50 or 100 years have passed. Everyone you knew is dead. Society has changed beyond recognition. You're a time traveler thrust into the future with no way to return. This raises a profound philosophical question. Is this really a round trip? Physically, yes, you can return to the same planet. But in every meaningful sense, the Earth you return to is a different place. You can't reunite with friends or family. You can't share your experiences with the people who saw you off. You're a stranger from your own future. This transforms interstellar travel into permanent exile. Once you depart, you never truly return home. This isn't a technical limitation. It's a fundamental consequence of how space-time works. Even if we had perfect technology, this reality would remain. But suppose you're willing to accept this. Suppose you build a ship capable of traveling at 90% of light speed using antimatter or some other miraculous technology. Would you be in the clear? No. Now you face another mortal danger: interstellar dust. The space between stars isn't completely empty. As I mentioned earlier, there's approximately 1 hydrogen atom per cubic centimeter on average. That sounds extremely sparse, and it is, but when you're traveling at near light velocities, even these scattered particles become dangerous. Here's why. At relativistic speeds, even tiny particles carry enormous kinetic energy. When they strike your ship, it's like being bombarded by high-energy cosmic radiation. A single hydrogen atom hitting your ship at 90% of light speed carries approximately the same energy as a bullet fired from a rifle. Now, imagine your ship being hit by billions of these bullets every second. Your ship's hull would erode rapidly. Worse still, the collisions would produce secondary radiation, creating a shower of high-energy particles inside the ship. This radiation would be lethal to any crew, even with heavy shielding. Protecting humans from this radiation would be extremely difficult. Some have proposed using a magnetic shield similar to Earth's magnetic field, which protects us from solar winds to deflect charged particles. But interstellar space also contains neutral particles that wouldn't be deflected by magnetic fields. And at truly high speeds, even photons, particles of light, carry enough energy to be dangerous. Starlight traveling toward you would be blue shifted, changed to higher wavelengths due to your velocity. Visible light would become ultraviolet or even X-rays. You'd be traveling through a radiation storm of your own creation. Then there are the larger dust grains, microparticles that occasionally float through interstellar space. A particle the size of a grain of sand hitting your ship at 90% of light speed would have the impact of a small nuclear bomb. A single one of these collisions could instantly destroy your ship. Detecting and avoiding these grains would be nearly impossible. You'd be traveling too fast to react. By the time you detected a grain in your path, you would have already struck it. You would need some kind of shield ahead of your ship, something sacrificial that absorbs impacts and protects the rest of the vessel. But this shield would have to be massive and constantly replaced or repaired. Some designs propose multiple layers of shielding, essentially spaced armor that vaporizes incoming particles before they reach the main hull. But this adds significant mass, which requires more energy to accelerate. The faster you try to go, the worse the radiation and dust problem becomes. It's another fundamental limit. Another reminder that the universe isn't designed for living beings to traverse at relativistic speeds. Now, let's talk about something that might seem like a solution: generation ships. If the journey is too long for a single human lifetime, why not send a ship large enough to sustain a population for generations? The first generation departs Earth, lives their lives on the ship, has children, and eventually dies. Their children grow up on the ship, never having known Earth, and eventually have their own children. This process continues for decades or centuries until the ship finally reaches its destination. The final generations colonize the new world, fulfilling the mission begun by their ancestors long ago. Generation ships have been a staple of science fiction for decades, and in principle, there's no physical law prohibiting them. They don't require exotic physics or impossible energy sources. They only require a very large ship with self-sustaining life support, and a population willing to spend their entire lives in transit. But when you examine the details, the challenges become overwhelming. First, consider the size. To sustain a human population for multiple generations, you need a lot of space. Humans aren't good at living in confined environments for long periods. Studies of long-term isolation, like simulated Mars missions, show that even small groups of highly trained people struggle with the psychological effects of confinement after just months or years. Now imagine entire generations being born, living, and dying inside the same closed environment. They never experience open sky, oceans, forests, mountains, none of the things humans have evolved to find comforting and stimulating. To avoid severe psychological problems, you would need to create an environment that feels spacious and varied. This means your ship needs to be enormous, perhaps kilometers in diameter, with multiple habitats, green spaces, maybe even artificial lakes. The larger the ship, the more mass it has, and the more energy required to accelerate it. Mass grows quickly. A generation ship could weigh millions of tons, maybe even more. Accelerating something like that to 10% of light speed would require amounts of energy that eclipse anything our civilization can currently produce, even with fusion or antimatter. The energy requirements might be prohibitive. Then there's the life support problem. Humans need air, water, food, and waste management. On short trips, you can carry these supplies or recycle imperfectly. But on generation voyages, you need nearly perfect closed-loop systems. Every atom of carbon, nitrogen, hydrogen, and oxygen must be recycled again and again for decades or centuries without significant losses. We know from experience with the International Space Station and other missions that current life support systems aren't perfect. There are leaks, inefficiencies, accumulation of contaminants. Over time, these problems compound. In a decades or centuries-long mission, even small inefficiencies eventually deplete your resources. You would need self-sustaining ecosystems, basically a miniature Earth ecosystem inside the ship. Plants to produce oxygen and food, microbes to break down waste, water systems for recycling. We've tried creating closed ecosystems on Earth, projects like Biosphere 2, and they haven't been completely successful. Maintaining a balanced, stable ecosystem for extended periods is extraordinarily difficult. Any imbalance, any species that goes extinct or proliferates, can destabilize the entire system. On a spaceship, you can't simply open a window to get more air or import food if your crops fail. You're completely on your own. There's also the maintenance and repair problem. Over decades or centuries, systems wear out, components fail, computers need upgrades, hulls develop microleaks. On Earth, we can manufacture spare parts, import materials, call in experts. On a generation ship, you have to be completely self-sufficient. You need to carry all the spare parts you might need, or you need onboard manufacturing capacity to make new ones. This means workshops, raw materials, tools, all adding mass and complexity. And you need people with the skills to use these tools: engineers, technicians, scientists. But how do you maintain that knowledge across generations? What if a field of expertise is lost because no one in a particular generation chooses to study it? What if critical information is damaged and no one remembers how to repair an essential system? Then there's the governance problem. How do you govern an isolated population for generations? What if political or social conflicts arise? On Earth, discontented people can move, form new communities, rebel. On a spaceship, you're trapped. There's nowhere to go. Conflicts could escalate to violence, potentially threatening the entire mission. You need stable social structures that can last centuries, maintaining morale, purpose, and cooperation generation after generation. That's something no human society has achieved on Earth for such long periods, without significant changes and upheavals. There's also the question of motivation. The first generation volunteers for the mission. They understand the purpose, believe in the goal. But what about later generations? They were born on the ship without choice. They never knew Earth. The destination planet is no more real to them than a story. Why should they care about completing a mission begun by people who died long before they were born? What if they decide they don't want to continue? What if they want to return to Earth, or go somewhere else, or simply stay where they are? And there are genetic problems. A small population on a generation ship would face inbreeding. Over time, this leads to genetic problems. You need a founding population large enough to maintain genetic diversity, probably several hundred or even thousands of people. But the more people, the larger the ship needs to be, the more resources it requires, the more energy needed to accelerate it. The ideal generation ship would essentially be a small, self-sufficient world, a massive ark capable of sustaining a complete civilization indefinitely. Building something like that would require resources and technology far beyond our current capabilities. And you would still have to accept enormous risks. A single catastrophic point of failure, a system malfunction, a radiation event, a disease, could wipe out the entire population. There's no rescue, no help. You're alone in the darkness between stars. Given these difficulties, some have proposed a different solution: cryogenic freezing. Instead of keeping a crew alive for centuries, why not freeze them? You suspend their biological functions, place them in some kind of stasis, and wake them when they reach the destination. This way, you don't need massive generation ships. You don't need self-sustaining ecosystems. You just need to keep the frozen bodies and the ship's critical systems functioning. The crew experiences the journey as a blink. They fall asleep on Earth and wake up in a new star system. Sounds perfect, right? The problem is that cryonics, as this technology is called, currently doesn't work. Not in the way we would need it for interstellar travel. We can freeze cells, small tissues, even some organs, and revive them with variable success. But freezing a complete human body and reviving it without damage is something we've never achieved. The main problem is ice crystal formation. When you freeze biological tissue, the water inside cells forms ice crystals. These crystals are sharp and rigid, and they pierce cell membranes, destroying the delicate structure of cells. When you try to thaw, you end up with cellular disaster. Cells are broken, their membranes are punctured, their organelles are damaged. The tissue essentially turns to mush. There are techniques called vitrification that attempt to avoid ice crystal formation. Instead of freezing, you convert the tissue into a glass-like vitreous state using cryoprotectants, chemicals that prevent crystallization. This works better than simple freezing, but has its own problems. Cryoprotectants are toxic in high concentrations. You need to perfuse the entire body with these chemicals, replacing blood and tissue fluids. Then you need to cool the body very quickly and uniformly, which is extremely difficult to do for something as large as a human body. Different parts of the body cool at different rates, leading to thermal stresses and cracking. Even if you successfully vitrify a body, storing it for decades or centuries presents challenges. You need to maintain extremely low temperatures, typically using liquid nitrogen at -196 degrees Celsius. Any temperature fluctuation, any warming even slight, can initiate crystallization or cause cracking. And then there's the reanimation process. You need to thaw or devitrify the body uniformly and quickly. Remove the toxic cryoprotectants without damaging tissues, restart the heart and breathing, and somehow restore brain function without loss of memory or personality. Currently, this is completely beyond our capabilities. Some companies offer cryogenic preservation services for people who die, freezing their bodies or just their brains, with the hope that future technology can revive them. But this relies on faith, not demonstrated science. No one has successfully revived a cryopreserved mammal, much less a human. Even if we assume future technology will solve these problems, there are other complications. During a decades or centuries-long voyage, the ship's systems need to function perfectly. A failure in the refrigeration system and the crew thaws prematurely, or worse, decomposes. You need power sources that last centuries, monitoring systems that never fail, and probably some kind of artificial intelligence or computers capable of managing the ship and responding to emergencies without human intervention. This raises another question. If you have AI or computers advanced enough to manage an interstellar ship for centuries, why send humans at all? This brings us to another proposal: robotic probes. Instead of sending humans, we send machines. Machines don't need air, food, water, or heat. They can withstand radiation that would kill a human. They can be designed to last centuries with minimal maintenance. And if they're damaged or destroyed, it's a scientific loss, not a human tragedy. In fact, robotic probes are our best bet for interstellar exploration in the near term. We've already sent them beyond our solar system. The Voyager spacecraft, launched in 1977, are now in interstellar space, more than 20 billion kilometers away. They're still transmitting data after nearly 50 years. They're testament to what human engineering can achieve. But the Voyagers are moving slowly, only about 60,000 kilometers per hour. At that speed, they would take more than 70,000 years to reach Proxima Centauri. To explore other stars in a reasonable time frame, we need faster probes. Breakthrough Starshot is a project that proposes doing exactly that. The idea is to build tiny probes, each weighing only a few grams, and accelerate them using Earth-based lasers. You attach a light sail, a thin, reflective sail, to each probe. Then you aim an array of powerful lasers at the sail. The pressure of the laser light pushes the sail, accelerating the probe. Calculations suggest you could accelerate these probes to 20% of light speed, fast enough to reach Proxima Centauri in approximately 20 years. This is revolutionary. You could send a probe today, and in your lifetime receive data and images from another star system. You could see exoplanets up close, study their atmospheres, search for signs of life, all without sending humans. But Breakthrough Starshot has its own challenges. First, you need to build a laser array capable of producing gigawatts of power focused with incredible precision on a tiny, fast-moving sail. This requires advances in laser technology, adaptive focusing systems, and power generation. Then you need to build the probes themselves. They have to be extremely lightweight, only a few grams, but still contain cameras, sensors, computers, and transmitters. They need to survive the acceleration, endure the 20-year journey through interstellar space, and have enough power to transmit data back across trillions of kilometers. This is miniaturization engineering at the extreme. And then there's the communication problem. At 20 light-years distance, a radio signal takes 20 years to return. You send your probe, wait 20 years for it to arrive, then wait another 20 years for data to come back. That's a 40-year commitment from launch to first results, and the signals will be incredibly weak when they arrive. You need large antenna arrays on Earth to detect them. Despite these challenges, robotic probes are feasible. They don't violate any laws of physics. They're difficult engineering projects, but not impossible. If humanity commits the resources and effort, we could send probes to nearby stars within the coming decades. But notice we're talking about small probes, not crewed ships. We're talking about exploration, not colonization. Probes can take pictures, gather data, search for life. They can't establish colonies, can't bring samples back, can't provide a backup home for humanity if something happens to Earth. For that, you need humans, or at least some way to transport life and technology to establish a settlement. And that's where the fundamental limitations become apparent. Let's talk now about something that sounds like science fiction, but actually has a basis in real physics: wormholes and warp drives. A wormhole is a shortcut through space-time, a tunnel connecting two distant points in the universe. In theory, if you could create or find a wormhole, you could enter one end near Earth and exit the other end near Proxima Centauri almost instantaneously. You wouldn't travel faster than light, you'd simply take a shortcut. The idea comes from Einstein's general relativity theory, which describes how gravity curves space-time. Certain types of curvatures, at least mathematically, can create these tunnel structures. The problem is that wormholes, if they can exist, are probably incredibly unstable. They would collapse as soon as you tried to use them. To keep a wormhole open, you would need something called exotic matter with negative energy density. This isn't antimatter, it's something even stranger. Matter that has repulsive gravitational properties. We have no evidence that exotic matter exists in usable quantities, if it exists at all. Some physicists believe the Casimir effect, a quantum phenomenon, might produce negative energy densities at very small scales. But scaling this up to macroscopic scales, enough to create a traversable wormhole, is completely beyond our technological reach, and possibly beyond what the laws of physics permit. Even if you could create a wormhole, it would have to be stabilized and positioned correctly, with one end near Earth and the other near your destination. How do you move the end to your destination? You would have to carry it there at conventional subliminal speeds, which brings us back to the original problem. Wormholes are theoretically fascinating, but practically far from a usable solution. They might as well be magic. We can't build them. We don't know if they can exist, and we have no way to stabilize or control them, even if we could create them. Then there's the warp drive, popularized by Star Trek, but actually based on a real physical concept proposed by physicist Miguel Alcubierre in 1994. The warp drive idea is to curve space-time around your ship, contracting space in front of you and expanding space behind you. The ship itself remains in a bubble of flat space-time, not moving through space in the normal way. Instead, space itself moves around you. Since space can expand or contract faster than light speed, there's no theoretical speed limit. You could travel faster than light without violating relativity, because technically, you're not moving through space faster than light. You're moving space itself. Sounds great, right? The problem is that, like wormholes, Alcubierre's warp drive requires exotic matter with negative energy density. The amounts of energy involved are astronomical. Initial estimates suggested you would need more energy than contained in all the mass of the observable universe. Later work has reduced the energy requirements, but they're still far beyond anything we can generate. And that's just the beginning. Creating and maintaining a warp bubble would require precise control over space-time itself. You would need to generate intense, highly localized gravitational fields, something we have no idea how to do. The bubble would have to move without destroying the ship inside it. There's concern that anything inside the bubble couldn't communicate with the outside, making it impossible to steer or control the bubble once it's in motion. And when you finally deactivate the warp drive, all the energy accumulated in front of the bubble could release catastrophically, possibly destroying your destination in an explosion of radiation. These are profound problems, not just engineering challenges. We're talking about physics we don't fully understand, phenomena we've never observed, and technologies that might be fundamentally impossible. Warp drives and wormholes are theoretically interesting, but practically offer no solution to our interstellar travel problem. So here we are, looking at all the options. Chemical rockets are too slow. Nuclear fission gets us to only a few % of light speed. Fusion, if we can make it work, perhaps 10 or 20%. Antimatter, even if we could produce and store it, maybe 50 to 90% of light speed, but with enormous technical challenges. Generation ships require massive resources and technology with immense social and biological risks. Cryonics doesn't work, at least not yet. Robotic probes are our best bet, but they can't colonize. Wormholes and warp drives are speculative and probably impossible. Do you see the pattern? Every potential solution faces fundamental barriers. We're not talking about problems we'll solve with better materials or faster computers. We're talking about limits imposed by the laws of physics, the amount of energy available in the universe, and the nature of space and time themselves. Now let's consider another dimension of the problem, the destination. Suppose we somehow overcome all these obstacles. We build a ship, accelerate it to a significant fraction of light speed, and arrive at Proxima Centauri after decades of travel. What do we find there? Proxima Centauri is a red dwarf, a type of star known for violent stellar activity. It emits powerful flares, radiation bursts that could sterilize any nearby planet. Proxima Centauri b, the exoplanet orbiting in the star's habitable zone, is much closer to its star than Earth is to the Sun, because red dwarfs are much dimmer. This proximity means the planet is probably tidally locked, always showing the same face to its star, just as the Moon always shows the same face to Earth. One side of the planet would be perpetually scorched, the other perpetually frozen. Perhaps there's a narrow strip between the two where conditions might be tolerable, but it's unclear. We also don't know if Proxima Centauri b has an atmosphere. The intense radiation from stellar flares could have stripped it away long ago. Without an atmosphere, the planet is uninhabitable, at least on the surface. No air to breathe, no atmospheric pressure, extreme temperatures. Even if there is an atmosphere, it could be poisonous, composed of carbon dioxide, methane, or other gases humans can't breathe. We would need to study the planet in detail before sending colonists. But doing so from Earth with telescopes has limits. The best instruments we have can only tell us the planet exists and estimate its size and orbit. Determining its atmosphere, surface conditions, whether it has water, whether it has life, requires close-up missions, probes that can study the planet in detail. And those missions require decades to get there, and decades for data to return. So even identifying a suitable destination is a long, difficult process. And Proxima Centauri is the nearest star. Most other stars are much farther away. To find a truly habitable planet, one with atmosphere, water, suitable temperatures, stable geology, we might have to look dozens or hundreds of light years away. The number of stars within 10 light years of the Sun is only a few dozen. Many of them are red dwarfs, like Proxima Centauri. Some are binary or multiple star systems, where stable planetary orbits are difficult. Some are too old or too young. Finding a planet truly similar to Earth, one where humans can live without extensive modifications or sealed habitats, may require searching hundreds of star systems. And each of those systems is light years away. The distances and timescales are simply crushing. Then there's the question of motivation. Why would we want to travel to the stars in the first place? There are several reasons people cite: scientific curiosity, the desire to explore, the search for extraterrestrial life, the dream of expanding human civilization beyond Earth. There are also practical arguments. Earth faces numerous existential threats: climate change, nuclear war, pandemics, asteroid impacts, supervolcano eruptions. Having colonies on other worlds could serve as backup insurance for the human species. If something catastrophic happens to Earth, humanity could survive elsewhere. This is the basket of eggs argument. Don't put all your eggs in one basket. It makes sense in principle, but establishing self-sufficient colonies in other star systems requires a level of resource commitment and technology currently far beyond us. Consider what it would take to make Mars, our nearest planetary neighbor, and most similar, a habitable place. Mars has no magnetic field, so cosmic radiation bombards the surface. It has a very thin atmosphere, mostly carbon dioxide, with surface pressure less than 1% of Earth's. There's no liquid water on the surface. Temperatures can drop to minus 125 degrees Celsius at night. The soil contains perchlorates, chemicals toxic to humans. To live on Mars, you would need sealed habitats, life support, radiation shielding, indoor food cultivation, water extraction and purification, oxygen production, and waste management. Essentially, you need to build and maintain an artificial Earth ecosystem inside protected structures. This is feasible, though difficult, because Mars is close. We can send supplies and equipment from Earth. Travel times are months, not decades. Communication has a delay of minutes, not years. If something goes wrong, there's a possibility of rescue or resupply. Now imagine doing the same on a planet light years away. No resupply, no rescue. The colony must be completely self-sufficient from the beginning. This means transporting not just people, but all the equipment, tools, materials, seeds, animals if necessary. Knowledge and technology to build and maintain a civilization from scratch. The mass involved would be enormous, far beyond what any propulsion system we've discussed could reasonably accelerate. And all this assuming you find a planet worth colonizing, one that won't kill you with its atmosphere, radiation, geology, or native biology. You could argue that if we have the technology to make an interstellar journey and establish colonies on hostile alien worlds, then surely we have the technology to make Earth habitable no matter what happens. If we can build self-sufficient habitats on other planets, we can build them on Earth, even in the worst possible conditions. It's much easier to live underground or under domes on Earth than to travel light years to live underground or under domes on another planet. This is a crucial point. Interstellar colonization isn't a practical short or medium-term solution to the existential threats we face. It doesn't save humanity from climate change or nuclear war or pandemics. By the time we have the technology and resources to establish interstellar colonies, if we ever do, we'll also have the technology to make Earth habitable no matter what. So the practical motivation, the backup insurance, crumbles under scrutiny. What about scientific curiosity? The desire to explore and learn. These are noble. Certainly humans are explorers by nature, but exploration can be done with robotic probes, as we've discussed. It doesn't require sending humans. And from a scientific standpoint, sending humans is less efficient than sending probes. Humans are fragile, require many resources, have complex needs. Machines don't. For every dollar spent sending humans, you could probably send 100 robotic probes. So what does that leave us? The romantic dream of expanding human civilization to the stars, of becoming a multi-planetary, multi-stellar, perhaps even multi-galactic species. It's an inspiring vision, one that has fueled science fiction for over a century. But when you face the cold, hard reality of physics, the scale of the universe, and the limitations of technology, the dream begins to feel more and more like fantasy. This doesn't mean we should never try. Human history is full of accomplishments that seemed impossible until they were done. But it's important to be honest about the barriers we face. Interstellar travel isn't just a difficult technical problem. It's arguably the hardest challenge humanity could ever attempt, requiring advances in physics, engineering, biology, and social sciences that could take centuries or millennia, if they're possible at all. Now let's talk about something more philosophical. Suppose we somehow solve all these problems. We build ships that can travel at relativistic speeds. We find habitable planets. We establish colonies. What does this mean for human identity? At near light speeds, time dilation means colonists age more slowly than people on Earth. If you send a colony to a planet 50 light years away, traveling at 90% of light speed, they might arrive in approximately 55 years according to Earth clocks due to acceleration and deceleration. But for them, thanks to time dilation, it might feel like only 20 or 25 years. They land on their new world, only slightly older than when they departed. But on Earth, more than 50 years have passed. Everyone they knew is dead or old. Society has changed, technology has advanced. If they try to communicate with Earth, signals take 50 years in each direction. A conversation requires a century. The colonists are no longer part of Earth civilization. They're a separate branch, evolving independently. Over time, under the influence of a different environment, perhaps different gravity, different atmosphere, different light patterns, they'll develop biological differences. After thousands of generations, they might be unrecognizable as humans in the sense we understand. They could become a different species. This could happen even without interstellar colonization. If we establish colonies on Mars, on Jupiter's moons, in asteroid belts, each will evolve differently. But the distance and isolation of interstellar colonization makes the division much deeper and more permanent. An interstellar colony isn't just an extension of humanity, it's the beginning of a new evolutionary line. There's also a profound paradox here. If interstellar travel is so difficult for us, it's probably equally difficult for any other civilization. This could explain the Fermi Paradox, the question of why we haven't seen evidence of intelligent extraterrestrial life. If there are billions of habitable planets in the galaxy, and if life is common, then there should be many civilizations out there. Some of them should be much older and more advanced than us. They should have colonized the galaxy long ago. We should see their signals, their structures, their technology, but we see nothing. The universe appears silent. Maybe the reason is that interstellar travel is simply too difficult. Even advanced civilizations can't overcome it. The laws of physics are the same for everyone. If you can't travel faster than light, and if distances are so vast, then each civilization is confined to its home star system, perhaps exploring a few nearby stars with probes, but never really spreading across the galaxy. This would mean the galaxy is full of isolated civilizations, each alone in their small bubble of space, unable to communicate or interact with others due to the vast distances involved. It's a lonely picture, but it could be reality. Or maybe civilizations don't last long enough. Perhaps there's some filter, some challenge civilizations face that most don't overcome. It could be technological, like developing weapons that can destroy entire planets. It could be environmental, like climate change or other ecological crises. It could be social, like political instability or economic collapse. If civilizations tend to destroy themselves or collapse before they can develop interstellar travel, then the galaxy would be full of ruins, not active civilizations. There's also the possibility that interstellar travel isn't desirable. Maybe advanced civilizations decide it's not worth it. Maybe they focus inward, building virtual worlds, exploring simulated universes, or uploading their consciousness to non-biological substrates. Maybe they find ways to satisfy all their needs without physically expanding. This is speculation, of course. We don't know why we don't see aliens, but the difficulties of interstellar travel certainly provide part of the answer. Maybe we're all just trapped, each civilization on their island of space, separated by oceans of vacuum that are practically impossible to cross. Let's return to Earth, to our small blue planet orbiting an ordinary star in an unremarkable galaxy. From our perspective, the universe is almost infinitely vast. There are approximately 200 billion trillion stars in the observable universe, each potentially with planets. The distances between these stars are so great that light, the fastest thing in the universe, takes years, centuries, millennia to travel between them. And yet here we are on this single world, looking outward and wondering if we can ever reach those other worlds. The answer, based on everything we know, is probably no. At least not in the foreseeable future. Not with technology we can realistically imagine. Not with physics we understand. The barriers aren't just technical. They're fundamental, inscribed in the very structure of space and time. Light speed is an absolute limit. You can't go faster, no matter how much energy you have. And at that speed, distances are overwhelming. The energy needed to accelerate ships to relativistic speeds is beyond what our civilization can produce. Maybe beyond what any civilization could produce without access to stellar or galactic scale resources. The dangers of interstellar space, radiation, dust, the need for shielding and life support, add layers of complexity that may be insurmountable. And all this assuming you find a destination worth reaching, a planet you can actually live on, which itself is a huge assumption. I'm not saying we should never try. I'm not saying we should give up on dreams of exploring the cosmos, but we should be realistic about what's possible. The grand exploration of the stars, the idea of humanity spreading across the galaxy, colonizing thousands of worlds, meeting alien civilizations, all of this may remain forever as fiction. The reality is that we're confined to this small corner of the universe, not by lack of ambition or ingenuity, but by the immutable laws of physics. Maybe that's not a bad thing. Maybe we should learn to appreciate the home we have, protect it, care for it, ensure it remains habitable for future generations. Maybe the lesson of the cosmos isn't that we should conquer it, but that we should understand our place in it. We're a young species on an ancient planet, orbiting an ordinary star in a galaxy filled with hundreds of billions of other stars. We're small, fragile, and probably alone for a very, very long time. If there are other civilizations, they're so far away we might never communicate with them, much less visit them. And that's okay. The universe doesn't owe us anything. It wasn't made for us. We simply exist in it for a brief flicker of cosmic time, trying to make sense of our existence. So why is it impossible for humans to travel beyond the solar system? Because the universe is vast beyond all comprehension. Because the distances between stars are so great that even light, moving at the fastest possible speed, takes years to cross them. Because the energy needed to accelerate a ship to significant fractions of light speed is beyond our capacity to produce. Because the dangers of interstellar space, radiation, dust, the cold vacuum, are hostile to life. Because we have no way to sustain humans during the decades or centuries-long journeys required. Because building generation ships or developing functional cryonics is beyond our current technology, and possibly any future technology. Because potential destinations are unknown, possibly uninhabitable, and would take generations just to discover. Because the laws of physics, special relativity, thermodynamics, energy conservation, all conspire to make interstellar travel extremely difficult, if not impossible. It's not that we're not smart enough or ingenious enough. It's that the universe is built in a way that keeps things separated. We live in a universe designed for isolation. Stars are separated by light years of vacuum. Galaxies are separated by millions of light years. The observable universe is limited by light speed and space expansion. Even if we could travel at light speed, which we can't, much of the universe would be forever inaccessible, carried beyond the cosmic horizon by the accelerating expansion of space itself. We're imprisoned in our small corner of the cosmos, not by choice but by design. And maybe that's something we need to accept. The universe is vast, beautiful, mysterious, but most of it is beyond our reach. We can study it, we can observe it, we can send robotic probes if we're lucky. But going there ourselves, walking on the beaches of alien worlds, gazing at strange suns that may remain forever as a dream. Tonight, we've journeyed through the barriers preventing us from reaching the stars. We've seen the impossible distances, the insurmountable energy requirements, the mortal dangers, and the fundamental limitations imposed by the laws of physics. It's not a happy story, It doesn't end with humans exploring the galaxy. It ends with the realization that we are, and probably always will be, confined to this small blue planet, and possibly our solar system if we're lucky. But there's beauty in that realization too. It reminds us that Earth is precious. It's the only home we'll have. And instead of dreaming about escaping to the stars, maybe we should focus on making this world the best place possible. Thank you for joining me on this journey through the limits of the possible. Good night, and may you find peace knowing your place in the cosmos, however small it may be.